kinetic energy of a particle moving along a circle of radius r is given. So let's say if I take this circle, that's the center of the circle. The radius of the circle is given as r. The kinetic energy is as square, so where a is a constant and s is the distance covered. Now if a particle is moving around a circle, it will experience an acceleration towards the center of the circle. So that's our centripetal acceleration, AR. So if v is the velocity of the particle, the centripetal acceleration AR, we know, if you have studied circular motion, then you know that the centripetal acceleration or the radial acceleration is v square over r. And then here, if you inspect the kinetic energy is increasing as distance covered is increasing. So obviously the velocity, the magnitude of velocity will also increase. Since the magnitude of velocity is increasing, in addition to the radial acceleration, we should have tangential acceleration as well. So there will be tangential acceleration in this scenario. So let's take that as AT. Okay, so this tangential acceleration is along the velocity. Now, how do I get this tangential acceleration? So if I take this kinetic energy as half mv square, I can write velocity of the particle as square root of 2a by m into s. So this is the speed of the particle along the circle. Now if I take a time derivative of this on the other side, I'll get acceleration, but this will be the tangential acceleration. So the tangential acceleration is dv by dt. So the velocity is tangential here. So this is square root of 2a by m into ds by dt. Now ds by dt is again velocity. So I have square root of 2a by m multiplied by velocity. So if I substitute velocity here, we get the tangential acceleration as 2a upon m into s. Okay, so we have a tangential acceleration. So how do we get the radial acceleration or the centripetal acceleration? All we have to do is take this velocity written as a function of distance covered and then substitute here. So the radial acceleration in this case will be 1 over r. So I'm squaring this term. So I'll have 2a upon m into s squared. Now the net acceleration acting on the particle will be a vector sum of these two accelerations. Because the angle between the radial acceleration and the tangential acceleration is always 90 degrees, so we can write the magnitude of net acceleration as square root of at square plus ar square. So here, if I, let's say, put them inside, so I have square root of 2a by m into s whole square plus I have 1 over r into 2a by m s square, and this thing gets squared. Okay, so from within the square root, if I pull the common factor, which is 2as by m, inside I'll be left with 1 plus, I think I have s here and then r inside the square function. So I have s over r whole square. Okay, now if I just multiply the net acceleration with mass, I should get the net force acting on the particle. Okay, so the net force acting on the particle is simply mass into the net acceleration. So that is 2as into square root of 1 plus I have s over r whole square.